Hello students, Professor Nugent here. In this video we are going to discuss binary dependent variables. In the last few videos we've been discussing how to think about including binary independent variables in a regression, and in this video we are going to flip the script and include the binary variable on the left hand side. So if we include the binary variable on the left hand side, what are we to do? Well folks, we can still use our usual tools of ordinary least squares, and if we do so, what results is the linear probability model. And in this video, we're going to focus on the linear probability model. Linear probability model is a very useful tool, but has a few caveats, and we'll get to the caveats at the end. And I would note at the top that there are other tools that are more commonly in practice for binary dependent variables, such as probit or logit. And if you are focusing on a binary dependent variable case, I suggest looking up my previous videos from introductory econometrics on probit and logit. All right, so let's get into the linear probability model, which is the best way to introduce how to get at estimating how to predict binary outcomes. When we predict binary outcomes, we are thinking about the conditional distribution as usual, expected value of y given x. But in this case, y only takes two values, and so what we end up predicting is the probability that y equals 1 given the values of x. And then that equals our usual linear regression model. Beta naught plus beta 1 times x1 through beta k times xk. So with this regression function, we are estimating the probability of success. Now, what does success mean? When there's this terminology of success in the discipline, that can be a bit confusing because success is not always the good outcome. Success is the outcome for the binary variable that is equal to 1. All right, but success does not need to be a good outcome. All right, so success, for example, for the binary variable deny equal to 1, where deny is the binary variable that is equal to 1 for mortgage applicants that have had their application denied. The outcome that is coined as success is the denial of the application. So that's deny equals 1. And so we have what can be a little bit confusing terminology where we think of success as being a good outcome, but here we have a case where it's actually not such a good outcome. But really what means success is that we have the outcome of interest occurring. Okay, so that's success. Success is that we see the outcome of interest for this binary variable. That's all that we mean by success. Okay, good. So this just implies, right, that the observation belongs to the group under consideration. Other examples might be in LF equals 1. And in that case, we're looking at in the labor force equals 1 if the individuals in the labor force and 0 otherwise. In that case, success might be a good outcome. Or maybe it's a bad outcome. Maybe you don't want to be in the labor force. That's, up to you. Good. So let's consider how the probability changes for changes in the explanatory variables. We can describe the change in probability, the change in the probability of success. So the change in probability that y equals 1 given the values of x. For a change in a given explanatory variable j, that's going to be equal to beta j times xj. So for a 1 unit change in xj, the change in probability of success is given by beta j. Right? And this is going to be in decimal form. This probability is in decimal form. All right. The difficult kind of thing with models that have binary dependent variables is that r squared is not an intuitive measure of fit. It's not a useful measure of fit, or a useful goodness of fit measure. we have two options instead of r squared. So the reason that r squared is not a useful statistic for goodness of fit, we are discussing that r squared is not an intuitive measure of fit. R squared tells us how well do the explanatory variables explain the sample variance in y. And so we can imagine a situation where r squared is equal to 1 and the explanatory variables perfectly explain y, so that you have a line that looks like a straight line where all of the data lie on that straight line. And that's just not what we're going to have with binary dependent variables, because our y is not measured on a continuous spectrum. And so we're not really explaining the sample variance in y. We can think of some better statistics for how well the model fits. We can think about the percent correctly predicted and pseudo r squared. Both are great statistics to refer to for your measures of fit when you have a binary dependent variable. Let's talk about how to calculate percent correctly predicted. To get percent correctly predicted, what we'll do is define a predicted value as yi tilde equal to 1 if the fitted value, so the probability that y equals 1, the fitted value yi hat is greater than or equal to 0.5. And define yi tilde equals 0 if yi hat is less than 0.5. And what we'll do is use the data on yi tilde and yi to obtain the frequency with which we correctly predict y equals 1 and y equals 0. So how often, or what is the relative frequency that yi tilde equals yi? That will give us the percent correctly predicted. You can obtain the pseudo r squared using Stata. Stata has a fitstat command that you will run after you run your regression. This will be a package that you'll need to install. With a binary dependent variable, there will necessarily be heteroscedasticity in the model. So we will not be able to, or we will violate the fifth linear regression model assumption, because the variance of y given x is equal to the probability of x times 1 minus the probability of x, because it's a binary variable, and that is equal to the probability beta naught plus beta 1 x1 through beta k xk times 1 minus probability beta naught plus beta 1 x1 plus beta k xk. So we see that the variance of y given x is a function of x. So we necessarily have heteroscedasticity in this model, in these models, unless there are no explanatory variables. So we're going to need to use heteroscedasticity robust T and S statistics. And we can do that using Stata. Importantly, OLS for the binary dependent variable models using the linear probability model the OLS estimates for this model are still unbiased as long as we satisfy the first 4 multiple linear regression assumptions. Right? We do not need homoscedasticity for our OLS estimates to be unbiased. Let's look at an example. An example might be predicting the probability of arrest prior to 1986 based on the proportion of prior arrests, average sentence served, months spent in prison since age 18 prior to 1986, months spent in prison in 1986, and the number of quarters that we're looking at a data set of men, so the number of quarters that the man was legally employed in 1986. So we have this equation. We're predicting AR 86 hat, that's the probability of arrest prior to 1986, and that is going to be equal to 0.441 minus 0.162 times PCNV. PCNV, this is the proportion of prior arrests, plus 0.0061 average sen. Average sen is the average sentence served, minus 0.0023 total time, and total time is the months spent in prison since age 18 prior to 1986, minus 0.0022 p time 86, and this represents the months spent in prison in 1986. Finally, minus 0.043 q EMP 86, where this variable takes on 5 different values. The number of quarters that the man was legally employed in 1986, so that can either be either 0, 1, 2, 3, or 4 quarters. Observe that positive variables mean that there's a higher probability of arrest prior to 1986. Negative variables mean that for higher values of those variables, there's a lower probability of arrest prior to 1986. Looking at just the intercept, 0.441, we see that the predicted probability of arrest for someone who has not been convicted, so there's no sentence, no time spent in prison, so all of these variables in the first 2 rows go to 0. The predicted probability of arrest for someone who has not been convicted and also not been employed for a whole year is 0.441. All right, so if all the variables are equal to 0, then the probability that someone has been arrested that person has been arrested is 0.441. I want to focus on this last term and interpret that coefficient. Observe that each quarter of employment decreases the probability of arrest by 0.043, so that a person employed for a full year has a 4 times 0.043, which is 0.172, lower probability of arrest than a person who was unemployed the full year, all else equal, which is a pretty important result. Now, this model that we have been working with does have caveats. This model only works well when the data is centered closely around the average, closely around the mean. The model will make poor predictions for data that is far from the mean, and so what you may find with the linear probability model is predicted probabilities that are negative or greater than 1 for values of the explanatory variables that are very far from the averages. In that case, it may be advantageous to use the probit or logit models, which we're not discussing in this class, but if this is a topic of interest for you, I suggest going back to my introductory econometrics videos where I discuss the logit and probit models in detail.